It is the summer of 1943, somewhere in northern France, and a man in a factory overall is doing something unremarkable. He has his back to the door, his shoulders slightly hunched, and he is pressing a small syringe into a grease nipple on the underside of a German half-track. The act takes perhaps 4 seconds. His hands do not tremble. He does not look around. When he is finished, he wipes his palms on a rag, picks up a crate, and walks away. What he has just introduced into that vehicle's lubrication system is not oil. It is not grease, at least not in any meaningful sense. It is a compound laced with one of the hardest naturally occurring substances on Earth. A fine-grained powder that, under the right conditions, transforms itself into something closer to a slow-motion shredder. The particles are microscopic. They are almost entirely invisible to the eye, and they are now working their way towards the engine bearings, the gearbox, the wheel hubs, every moving surface in the machine, where they will begin, quietly and methodically, to destroy it from the inside. The Allies called it carborundum. The scientists knew it as silicon carbide. The Germans, when their vehicles began breaking down in bewildering and inexplicable numbers, had no idea what it was or where it was coming from. This is the story of a sabotage weapon so elegant, so devastatingly simple that it required no explosives, no timers, no fuses, and no courage in the conventional sense of the word. It required only access and a small tin of powder that could fit inside a coat pocket. Conceived in the clandestine laboratories of Britain's Special Operations Executive, refined by chemists who rarely left the English countryside, and delivered by ordinary men and women working ordinary jobs in occupied Europe, it was a weapon aimed not at the armour of Germany's finest tanks, but at their insides, at the part of the machine that no amount of steel plating could protect. Because the Tiger tank could survive an anti-tank round, it could absorb artillery fire, it could crush hedgerows, ford rivers, and shrug off almost everything the Allies threw at it in direct combat. But it could not survive the slow destruction of its own lubrication, and that, it turned out, was the key. By 1942, the Wehrmacht possessed something the British military feared with a very particular kind of dread. The Panzerkampfwagen 6, the Tiger, was not simply a superior tank. It was a statement of industrial and engineering confidence at a moment when Germany still believed it could outbuild and outfight the entire Allied world. The vehicle weighed approximately 57 tons in combat-ready configuration, carried armour up to 100mm thick on its frontal glacis, and was armed with an 88mm gun capable of destroying virtually any Allied armoured vehicle at ranges that Allied guns simply could not reciprocate. In Tunisia in early 1943, British tank crews reported engaging Tigers at distances of less than 600 metres with 6-pounder anti-tank guns, watching their rounds deflect off the frontal armour like stones skimming water. The psychological effect was profound and immediate. Infantry commanders who had never shown particular anxiety about the prospect of enemy armour began writing urgently to their superiors. Something had to be done. The conventional military response was to develop better guns and better tanks, and the British were working on both. The 17-pounder anti-tank gun, rushed into service in late 1942, was a genuine answer to the Tiger in direct engagement, but there were never enough of them. They were difficult to conceal, and the Tiger, precisely because it was so valuable, was rarely committed to the sort of frontal assault that made it vulnerable to prepared defensive positions. The Germans understood their machine's limitations as well as its strengths. They knew that a Tiger with a broken track or a failed engine was worth nothing, and they were careful about where and how they deployed them. But there was something that the Germans could not so easily control. Every Tiger, every Panther, every half-track and staff car and supply lorry in the Wehrmacht's vast motor pool required regular lubrication. The engines demanded oil, the gearboxes demanded grease, the wheel hubs, the turret rings, the traverse mechanisms, all of it required constant, careful maintenance by men who were not always able to verify the integrity of every tin and every syringe used to keep the machines running. Germany's supply chains stretched thousands of kilometres. Their vehicles moved through occupied territory, and occupied territory was full of people who hated them. The question facing British planners was not whether sabotage was possible. It was whether there existed a method of sabotage so simple, so undetectable, and so widely replicable that it could be taught to factory workers, railway mechanics, and resistance volunteers with minimal training and minimal risk. Explosives were obvious. Explosives were dangerous to handle, dangerous to acquire, and when they went off, immediately identifiable as acts of sabotage. What was needed was something that looked like nothing at all, something that looked like lubrication. The men and women tasked with solving this problem worked in a series of requisitioned country houses scattered across the English home counties. The most important of these facilities, known within the SOE's administrative structure simply as Station 9, was located at Aston House near Stevenage in Hertfordshire, a Georgian pile that had been transformed behind its genteel exterior into one of the most inventive weapons laboratories in the world. Here, chemists worked alongside engineers, former burglars, and industrial sabotage specialists in conditions of strict secrecy, developing devices that ranged from the dramatic to the almost laughably mundane. The abrasive grease compound that would eventually be used against German armour was not a single dramatic invention. It was the refinement of a principle that was in itself almost insultingly straightforward. If you introduce a highly abrasive material into a machine's lubrication system, the lubricant ceases to protect the moving surfaces and instead begins to grind them away. The harder the abrasive, the faster the destruction. The finer the particles, the more insidious the process, because fine particles pass through filters that would trap larger grit, spread more evenly across bearing surfaces, and generate heat that accelerates the very wear they are causing. Silicon carbide, carborundum, had been commercially manufactured since 1893, when an American chemist named Edward Acheson discovered that he could produce it by heating a mixture of silica and carbon to extreme temperatures. The resulting compound registered a 9 on the Mohs hardness scale, placing it just below diamond and well above steel. It was already widely used in industry as a grinding and polishing abrasive, and it was manufactured in considerable quantities throughout the industrialized world. It was, crucially, entirely unremarkable. A small container of it would not attract attention in an industrial setting. It resembled fine white flour or powdered chalk. It was odourless. It left no trace visible to the naked eye once introduced into a dark, oily system. SOE's technical teams worked out the optimal grading of the powder, fine enough to pass through standard grease nipples without blockage, coarse enough to cause rapid mechanical damage once distributed across bearing surfaces. The compound was then mixed with standard grease to create what was, to all outward appearances, a perfectly normal lubricant. The containers were prepared to match, wherever possible, the appearance of legitimate German military greasing supplies. Instructions for its use were developed in multiple languages and reduced to the simplest possible terms. The carborundum grease was ready mixed with base grease at roughly a 1:3 ratio by volume, with the abrasive content calculated to begin causing measurable damage within approximately 200 kilometers of normal vehicle operation, far enough from the point of application that the cause of failure would not immediately be apparent, but fast enough that the destruction would occur before the next scheduled maintenance interval. In a vehicle engine subjected to normal operating loads, silicon carbide particles between 50 and 100 microns in diameter, roughly the thickness of a human hair, would migrate through the oil circulation system, embedding themselves in soft bearing surfaces and scoring cylinder walls with a precision that no saboteur with a hammer could replicate. The compound could be introduced through any grease nipple on a vehicle's chassis, through the oil filler cap of an engine, through the gear oil ports of a transmission, or through the lubrication points of wheel bearings. Every one of these access points existed on every vehicle in the German motor pool. Every one of them was, by definition, designed to be opened and serviced by maintenance workers. The SOE did not deploy this weapon through a single dramatic operation. It spread it quietly and persistently through the existing networks of resistance workers, factory employees, railway mechanics, and garage hands who were already working, sometimes at extraordinary personal risk, to slow the German war machine through 1,000 small acts of obstruction. The carborundum compound was supplied in bulk via parachute drops to resistance networks across France, Belgium, the Netherlands, Norway, and occupied Eastern Europe. Agents were instructed in its use during clandestine training sessions. Workers in German requisition garages and maintenance depots were provided with the compound and briefed on exactly which points of a vehicle's lubrication system would produce the most rapid and the most difficult to diagnose failure. In France alone, estimates suggest, and here the historical record becomes genuinely difficult to verify, since resistance networks were by their nature clandestine and record-keeping was both dangerous and inconsistent, that hundreds of vehicles were treated with abrasive compounds during the course of the occupation. Railway locomotive bearings were a particular target, and SOE files document numerous instances of locomotives failing with seized bearings within days of maintenance performed by resistance-connected workers. The same principle applied directly to armoured vehicles, and there are documented accounts in SOE operational records of German armoured units reporting inexplicable mechanical failures at rates that significantly exceeded what could be attributed to normal operational wear and combat damage. The genius of the weapon was precisely what made it so difficult to document with certainty. A seized engine bearing looks like a seized engine bearing. The failure modes are consistent with what happens to any machine that is poorly maintained, overloaded, or simply run until it breaks down. German technical officers investigating mechanical failures would, in many cases, have attributed them to the extraordinary demands being placed on their vehicles, to the quality of wartime production components, or to the simply extraordinary fragility that the Tiger and Panther had already demonstrated in routine operation. The Maybach HL230 engine fitted to later Tiger is, and the Panther was, under the best of conditions, a unit that required rebuilding approximately every 1,000 to 1,500 kilometres. In the brutal conditions of the Eastern Front, that figure was frequently much lower. A Tiger with a seized gearbox or a spun crankshaft bearing was in most cases simply a Tiger that had broken down. Germany had a lot of those. If you are finding this interesting, a quick subscribe helps more than you know. The Tiger I's mechanical vulnerabilities were not secrets known only to the Allies. The German military's own assessments of the vehicle were frequently scathing on this point. The tank's final drive units, a pair of epicyclic reduction gears located at the front of the hull, through which all the power of the engine was transmitted to the tracks, were chronically overloaded. The vehicle had been designed to a weight specification of approximately 45 tons. By the time it entered production, it weighed closer to 57. The drivetrain, never updated to reflect this increase, was consequently operating permanently beyond its design limits. A Tiger in good mechanical condition, driven carefully on good roads, might achieve a range of 140 kilometres on a full tank of petrol before requiring refuelling. Cross-country range was frequently less than half that. The Army's own maintenance guidelines stipulated 10 hours of workshop attention for every hour of active operation, a ratio that, under active combat conditions, was essentially impossible to achieve. What the carborundum compound did in this context was take a machine that was already fragile and make it more so. It did not create failures from nothing. It accelerated failures that were in many vehicles already waiting to happen. The compound was most effective not against vehicles that were already being carefully maintained and inspected by experienced mechanics, but against vehicles in the field, moving through occupied territory, serviced by a mixture of German technical personnel and locally conscripted workers who might, or might not, be supplementing the official lubricant with something considerably more destructive. The comparison with German attempts at equivalent sabotage is instructive, if somewhat lopsided. The Abwehr, Germany's military intelligence service, and the SD both ran sabotage networks during the war, but their efforts against Allied industrial and military infrastructure never achieved anything comparable to the systematic degradation that the SOE managed through its abrasive compounds. The Germans were, by 1943, fighting on multiple fronts with declining resources and an industrial base being steadily reduced by Allied bombing. Their capacity for the patient, sustained kind of sabotage that the carborundum operation represented, requiring reliable networks, consistent supply, and the cooperation of hundreds of individuals over years, had been severely limited by the war's strategic trajectory. American military planners observed the British abrasive compound program with considerable interest, and the OSS, the American equivalent of the SOE, incorporated similar sabotage techniques into its own operational doctrine. A document produced by the OSS during the war noted that silicon carbide, available commercially and entirely innocuous in appearance, was more effective than sand as an engine abrasive because its hardness was so much greater. The OSS observed that enough carborundum powder to destroy a heavy vehicle's engine could be carried in a single trouser pocket. Assessing the precise historical impact of the carborundum program is, to be frank, an exercise in informed speculation rather than confident conclusion. The nature of the weapon made it almost impossible to attribute specific vehicle failures to specific acts of sabotage. German maintenance records from the period show catastrophic failure rates in armoured vehicles, but the causes were multiple and overlapping: design flaws, production quality declining under wartime pressure, overloading, inadequate maintenance, and the simple mechanical attrition of vehicles being used far beyond their intended operational parameters. What can be said with confidence is that the SOE's scientific directorate and the resistance networks it supported introduced a principle of mechanical sabotage that was genuinely novel, not in the basic concept of abrasive contamination, which was as old as industrial machinery itself, but in its systematic application as a strategic weapon. The program was, by any measure, extraordinarily cost-effective. The materials were cheap, widely available, and legally manufactured. The delivery mechanism required no explosives and no sophisticated technical knowledge. The risk to the individual agent was present but manageable, far lower than the risk of planting explosive charges or cutting railway lines, and the cumulative effect of dozens or hundreds of small acts of contamination spread across a vast occupied territory over a period of years was a steady, quiet bleeding of German mechanical capability that conventional military action alone could not have produced. The psychological dimension deserves mention as well. For German vehicle crews and maintenance officers, the experience of unexplained mechanical failures, of vehicles that should have been running grinding to a halt, of engines that had been recently serviced suddenly seizing, introduced a corrosive uncertainty into everyday operations. Every maintenance worker became a potential saboteur. Every tin of grease became a potential weapon. The effort required to police this possibility, to verify the integrity of every supply in every depot across occupied Europe, was enormous, and it was effort diverted from the actual prosecution of the war. The surviving documentation on the SOE's abrasive compound work is held at the National Archives at Kew, in files that remain classified for decades after the war and are still not entirely complete. The specific operational details of how the compound was manufactured, packaged and distributed are partially redacted in publicly available records. What remains gives a picture of a program that was considerably more extensive than its almost complete absence from popular military history might suggest. Return, for a moment, to that factory in northern France. The man in the overalls has long since walked away. The half-track will start normally. It will drive normally for days, perhaps weeks. The driver will notice nothing. The maintenance crew, if they bother to inspect the vehicle at all during that period, will find nothing obviously wrong. The grease nipples will look fine. The oil levels will be correct. And then, on a road somewhere in occupied France, or perhaps on a railway siding, or in a depot lorry park, something inside the machine will change. A bearing surface, worn slightly faster than it should have been, will reach the point of failure. The temperature will rise. The metal will start to seize. And what had been, that morning, a functional component of the German war machine will become dead weight. This is what the Carborundum program achieved when it is understood in the aggregate. It did not stop the Tiger in its tracks on a single dramatic morning. It did not destroy a single vehicle in a flash of fire and smoke that could be filmed and cited and celebrated. It worked instead the way erosion works, the way water works on stone, patient and invisible and utterly relentless, converting the mechanical confidence of the Wehrmacht into uncertainty, delay, and cascading breakdown, one seized bearing at a time. The Tiger tank remains one of the most iconic weapons of the Second World War. Its armour, its gun, its sheer physical presence on the battlefield all contributed to a legend that has never quite faded. But the legend tends to focus on what the Tiger could do to its enemies. It is less comfortable with what was being done to the Tiger, not by opposing tanks or anti-tank guns or Allied air power, but by ordinary men and women with powder in their pockets and hatred in their hearts, who understood cannot fight, and a machine that cannot fight. And a machine that cannot fight, no matter how formidable its specification or how fearsome its reputation, is nothing more than very expensive scrap. The Germans built 1,347 Tiger I tanks between August 1942 and August 1944. More were lost to mechanical failure and were abandoned by their own crews than were destroyed by direct enemy fire. Some of those failures were design flaws, some were the inevitable consequence of wartime production under pressure, and some, how many exactly, will never be known, were the legacy of a tin of white powder mixed quietly into the grease that was supposed to keep the machine alive.